Hello everyone and welcome back to the channel. Today we are going to break down this particular 4-bit arithmetic circuit here. This circuit which you see here is capable of performing 8 different arithmetic operations. We'll trace the data flow for each one so you can see exactly how a computer does its math. Our 4-bit circuit consists of 4 identical stages, one for each bit, where I equals to 0 to 3. So at the core of each stage is a full adder labeled Xi, Yi and Ci. This is where the actual addition happens. We have 4-bit input registers A, which has A3 to A0, and B, which has B3 to B0. Notice that AI goes straight to Xi here. A0 goes to X0, A1 goes to X1, A2 goes to X2, and A3 goes to X3. And then these A inputs directly go into the full adder. Now, the input yi to the full adder is controlled by a 4 into 1 multiplexer. This multiplexer selects which modified version of bi to send to the adder. And the entire operation is actually controlled by 3 control signals: S1, S0, and Cin. So S1 and S0 are the control lines or selection lines for the mux, and Cin is the initial carry to the least significant bits full adder. The key to performing various operations in the mux controlled by S1 and S0. So we should take a look at what the mux sends to yi. So when the input is 0 and 0, basically the mux input 0 is selected and then sent to the output, which means b the value of b0 or b1 or b2 or b3 is selected to the output. Whenever the status lines s1 and s0 are 0 1, the complement is selected for the value y or the input y, which means the output line 1 is selected, which is the complement of b0, b1, b2 and b3 here. And when the selection line status are 1 and 0, then 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 the input number 2 is selected, which is extracted from the value 0 here. And then when it is 1 1, then the input number 3 is selected, which is the value that is extracted from complementing 0, which means it's 1. So since the full adder computes the value of a plus y plus c in, by changing the y and c in, we can get 8 different arithmetic operations here. First of all, we'll start with the add operation, which is a plus b. To perform a simple add or a plus b, we set the status lines to 0 0. If the status lines are set to 0, this selects the input b. So y will be equal to b. We also set the initial carry to 0 here, and the full adder computes d equal to a plus b in place of y, and then c in is 0. So basically it will compute a plus b. Simple addition. Next is add with carry. If we keep s1 and s0 as 0 as earlier and only add 1 in place of this carry bit, then the output is a in place of a, b in place of y, and 1 in place of c in, which means a plus b plus 1, basically meaning add with carry. So the third operation is a plus b complement, which is also known as subtract with borrow. So for this we use the complement method. So basically we are setting s1 equals to 0 and then s0 equals to 1. So whenever 0 and 1 are present in the selection line, then basically the input 1 is sent to the output. So what is in input 1? This is the complemented value of b, which means it's b complement. Since Cin is 0, so the result is A plus B complement. Now let's go to A plus B complement plus 1. Again, the value of S1 and S0 are 0, 1, which means the input 1 is selected, which is B complement. A is already gone from here, so A plus B complement, and then in place of Cin we pass 1, which means it's A plus B complement plus 1. Next, we move to transfer A. To simply transfer the value of A, we need the full adder to compute A plus 0. So, if we keep the value of S1 and S0 as 1, 0, the input line 2 is selected. So, what is in input line 2? It is basically the value 0. So, the output is also 0, which means here we get A, here we get 0, Cin is 0. So, basically the output is only A. Now, if we want to implement an incrementer here, we basically need to add the carry in bit, or basically send carry in equal to 1 here. That will work it as an incrementer. To decrement A or subtract 1 from A, we use the 2's complement method again. We set S1 and S0 as 1 and 1, which forces the Y to select the input number 3 as output, which means the input number 3 is 1. So every mux generates the output of 1 and then sends it to Y0, Y1, Y2 and Y3. When we say A minus 1 in 4-bit, we basically meaning A minus 0001. And if we do the 2's complement of 0001, we basically get A plus 1111, which is equivalent to D equal to A minus 1 again. And finally, we have transfer A again. So if we keep S1, S0 as 1, 1, and we set C in as 1, the result is A plus 1 plus 1. And for a 4-bit system, adding 1 plus 1 with overflow is the same thing as adding 0. This is equivalent to another transfer A operation, demonstrating a slight redundancy in the circuit's function table. So there you have it. By simply changing the three control signals S1, S0 and Cin, this relatively simple 4-bit circuit can perform 8 critical arithmetic micro operations, 2 forms of addition, 2 forms of subtraction, increment, decrement and transfer. And this fundamental circuit implementation shows the power of using a select mechanism or the mux to repurpose a basic adder circuit for a variety of tasks. It's a core concept in computer architecture. So if you found this breakdown helpful, please hit that like button and subscribe for more deep dives into digital logic and computer science. Let me know in the comments which logic gate or circuit should I explain next. Thanks for watching and I'll see you in the next one.